All right, it's like really stuffy in here, isn't it? All right, well, we have an exam in 48 hours.
I was dreaming of 72, but we had to reduce it to 48.
Yeah, so that exam, we'll talk about it at the end of class a little bit. I'm going to bring up one of my old exam reviews. It's similar to the material. It's not exactly the same, but it'll give us some idea of what to expect. We need to continue with related rates, though, and then we're not going to tackle the more complicated problems on related rates. Well, we're not going to be tested on the more complicated ones. On the next exam, exam 3, I'll probably have a complicated related rate problem. I've even thought about maybe sending you home with one or two of them. We'll see. Okay, so let's talk about related rates. We had done the problem here with the expanding sphere. And let's just kind of pick up with the next example, which is, can y'all read that okay? Make it a little bit bigger. Let's see if that, okay, so we're going to do another problem with an expanding sphere, but let's read through, well, should we look at the other one just to see what the difference in the questions?
I think it's just the rate.
There we go. So this is the one I gave you before. Said if the radius of a sphere is increasing at a constant rate of 2 feet per second, how fast is the volume increasing when the volume is 36 pi cubic feet? So the radius was growing at a constant rate, and we wanted to know at a specific instant in time how fast the volume was increasing. All right, now let's compare that to this problem. If the surface area of a sphere is increasing at a constant rate, so not the radius growing at a constant rate, the surface area is increasing by the same amount at every point in time, then how fast is its volume increasing when the volume is 36 pi cubic feet again? So I don't have a picture? I don't have a picture of this. Okay, well, oh well. All right, so let's go through the setup on these. The way that I like to encourage you to look at these problems is by drawing what I refer to as like a general picture. And remember, in this general picture, you're going to have whatever's happening and imagining that everything is in motion. So you can't fix anything, all right? So we're going to have just a sphere over there. And then we're going to be looking at the moment or the instant where we take that snapshot, right? Where we say, okay, right at that instant, what's going on? And then we're also going to try and write down any information we're given, and we want to write down what we want. And eventually, we're going to want to get an equation, all right, that we're going to differentiate. So let's just draw a picture of our general situation. We've got a sphere. Draw a circle with this little like elliptical thing in the middle of it, little dot in the center. So we've got this sphere, right? And it's growing. It's getting bigger and bigger. Now the difference between the general picture and the moment or instant picture is that at the instant in time we're talking about, the volume is fixed to be 36 pi cubic feet, right? So it's frozen. Over there, the volume is actually changing, right, in the general picture. And also remember that when you're doing this, you don't have to do any one particular thing first, okay? You can do anything as long as you try and get it all together. So how about anything I'm given? I'm given what's increasing at a constant rate? The surface area, right? The surface area is increasing at a constant rate. And when we say a constant rate, when you see the word rate, you should be thinking speed, you should be thinking derivative. So we are given information about the derivative of the surface area. Agreed? Now I'm going to call the surface area of this sphere A. Capital A for area. Everyone understand I mean surface area? Yes? Okay, so I'm given dA dt. The change in area with respect to time for this sphere is 20 square feet a second. Now, what am I interested in determining? What is the question asking me to find? What do I want? How fast, right? How fast its volume is increasing. So it doesn't want volume, it wants the change in volume, right? The derivative of the volume. It wants dV dt. And at what exact moment do we want this? So we normally will write what we want and then at some specific point. So is it volume or area? When I took that snapshot. At V equals 36 pi cubic feet. So I want to know how fast is the volume changing with respect to time at exactly the moment that the volume is 36 pi. Understand? Okay. Now I think I've got a pretty decent setup here. I need to come up with an equation now that does what?
A derivative that tells you what the volume is at 36 pi feet cubed, at a volume of 36 pi feet.
Well, yes, the equation will eventually be able to solve this, but I told you last class, when you're looking for this equation, you just have to look back at the geometry of the problem, or whatever is given to you in the problem, and try and connect what two variables together? Area and volume, right? You need to somehow come up with the relationship between area and volume of a sphere. And that's going to be somewhat problematic, because we have a few formulas on our formula sheets. Let's look at those formulas. This will be kind of a side note here. What formulas do we have in terms of spheres? We have a volume formula, right, which is what? 4/3 pi r cubed, right? And then we have an area formula, right? And what is that? It's on your sheet, 4 pi r squared. I would make sure that you have that sheet. You're allowed to have that on the test. It would not be wise for you to not bring that to the test. And remember, you're not allowed to edit those. You can't like write your own little scrap formulas on there. Now there will be a few times later on this semester where I tell you can add this to your formula sheet, but I haven't said that yet. All right, so these are the only two formulas we have, right? Okay. Well, this one connects V to radius, right? Volume and radius, and this one connects area to radius. I'm trying to connect area to volume. So I don't have a formula that's provided to me that does that. Do y'all agree? Yes. So how can I do this then? Well, these are equations, right? Yes. So if we have equations, we are free to manipulate them however we want. So here's what I'm going to do. I'm going to take this equation right here, and I'm going to solve it for r. And then I'm going to take that expression and plug it into this equation. And then I will have an equation that has just volume and area. So let's see how this happens. If I solve this for r, do you agree I'm going to do, let's do it this way, area over 4 pi equals r squared. You'll agree with that? Just dividing both sides by 4 pi. And then take the square root on both sides. So square root of area over 4 pi equals r. Now it's supposed to be plus or minus, but it's the radius of a sphere, so it's only going to be positive. We good? Now I'm going to take this and I'm going to plug it into that right there, r, and then cube it. Right? So I'm about to write this formula right here. Here it is. volume equals 4/3 pi, and then the square root of area over 4 pi cubed. And that is an equation that has area and volume together, right? So that's my equation. It's not pretty. But, you know, sometimes life is just like that, right? Questions? Okay, I'm going to try and clean that equation up a little bit because I have to differentiate this, don't I? And there's a lot going on with roots and cubes, and I'm going to just try and clean it up a little bit. This is what makes this problem complicated, okay? This is what makes this problem different than the previous one. In the previous one, we just worked with this formula and we differentiated and we were clear to go. It wasn't that big of a deal. But this coming up with the equations a little bit nasty, and then what we get as a result isn't pretty to look at either. Let's see if you agree with this. 3/2, is that the same? Right, square root means raise this to the 1/2 power. And then when you raise that to the third, it's equivalent to raising it to the 3/2. So that okay? I'm going to do a little bit more. Volume equals 4/3 pi. And then I'm going to actually split this up. I'm going to do area to the 3/2. And then I'm going to do 4 pi down here to the 3/2. Now, the reason I'm doing this, the reason I'm continuing to clean this up, is because I noticed that I have like a 4 pi over here, and I have a 4 pi down here. Yes? So somehow these can come together and kind of clean up. This is all a constant, isn't it? Okay. Let me do this. See if this helps. 1/3 times 4 pi to the first power over 4 pi to the 3/2 power times a to the 3/2. All right, is that the same thing? See, if I take this 1/3 and just pop it out like this, and I take the 4 pi, it's 4 pi to the first power on top. On the bottom, I have 4 pi to the 3/2 on the bottom. Yes? And then the a to the 3/2 that's on top, I can just slide it out to the side. So all I'm doing right now is just algebraic manipulations. I have not taken any derivatives yet, right? There's no calculus in this yet. Now, what is 4 pi to the first power over 4 pi to the 3/2? You're supposed to take this exponent and subtract this, right? So that's really 4 pi to the negative 1/2? Yeah. Negative 1/2? Let me continue. So we have volume equals 1/3 times 4 pi to the negative 1/2 times a to the 3/2. And this is really volume equals 1/3 root 4 pi times a to the 3/2. Okay, so all I did was drop that back down. This means square root, negative power means drop it down. So that's it. This is all a constant, right? And then I have a to the 3/2. Questions? Is this making you feel ill?
Yes.
Okay. Okay, now we have a cleaned up version of an equation that connects volume and area together. So now what I'm going to do is differentiate this. And I'm differentiating with respect to time, with respect to little t, because remember I wanted dv dt and dA dt, right? Those were the two things in the problem. Actually, I was given dA dt and I want dv dt, so everything's differentiated with respect to time. So let's go ahead and do this. Derivative of the left side, dv dt, right? trying to decline this call. There we go. All right, what about the constant? Just bring it down, right? Comes for the ride. And then we take derivative of a to the 3/2. So we have to use the power rule and the chain rule here. So first the power rule, 3/2 comes out. A to the, subtract 1 from this, right? So should be positive. 3/2, take away 1, should be 1/2. Okay, I'm just going to check this because this is from the college.
It's a test of the system.
Oh, okay, that's what it is. All right, just want to make sure. All right. So this okay? Yes? Am I done?
No.
No, I need what tacked on to the end of this? dA dt. So that's your chain rule, right? You're taking derivative of something to a power. Power comes out, reduce the power by 1, and then take derivative of what's here with respect to time, dA dt. And I'm happy to see this here, right? Excuse me. I'm happy to see this because this is what I was given, right? The rate at which the volume or area was increasing. I want dV dt. The only thing I don't have, so let me put some little check marks. I'm happy to see that because that is what I'm given, right? Given that. I want this, so I'm happy to see that. The area is the only thing in the equation that I don't have right now, right? The area is the only thing I don't have. So can I get the area? See, at this point, and only at this point, I can start holding everything constant. After the differentiation, did I make that clear enough last time? That you cannot plug in the snapshot constants, that 36 pi. You can't plug that in until after you've taken the derivative. All right? So I need to figure out the area. So let me go back to my picture, my snapshot picture, my instant picture, where I had the circle, or sphere, sorry, and I had that the volume was 36 pi cubic feet. So at this particular instant in time, do I know what the area is? I'm going to have to work for it, right? I'm going to have to work for it. So the only formula I have for area was 4 pi r squared. Oh my gosh, stop. All right, so area is this, right? So if I had the radius of the sphere, I would be good. It's ridiculous. Stop. Go away. All right, so could we get the radius? Yes? Yeah, because we have this. So this right here, 36 pi, is equal to 4/3 pi r cubed, right? Now, if you check back in your notes from last class, did we actually solve for the radius? We did? What was it? I don't feel like going through that. What was the radius here? It was 3? 3 feet. Okay, so that's from last class. Just solve for r in that equation. So now, if I know the radius is 3 feet, I can come down here to my area formula and get the area, right? So using that, area is 4 pi times 3 squared, which is 36 pi. Now, it's just coincidental that they're the same value, okay? Because this 36 pi cubic feet is not the same as 36 pi square feet. I mean, it's the same number, but they represent two different things, a volume versus an area. If you had any other radius, it would be different, all right? Okay, we good? Now back to this. Now back to this. We're ready to try and solve. And remember, we're trying to find this right here, aren't we? That's what we want? No? Oh, we want, oh, volume. We want this one, sorry. We want this. Now look, let's say that we had wanted this. I would not try to isolate this. In other words, I would not try and get this by itself. What I would do is I just plug everything in and then move numbers over to the other side. I would not try and manipulate this algebraically. But we're not looking for this. All right. So let's plug everything in. We should be ready to go. dV dt should be 1 over 3 times 4 pi, square root of 4 pi times 3/2 times what? The square root of 36 pi. That's what this meant, right? And then times dA dt, which was 20. Yeah, and I'm not putting any units. So let's try and clean this thing up. I see 3's cancel here. I see this 20 can become a 10 because of that 2. And I have 36 pi under a root over 4 pi under a root. So I can put those together under a single root. In other words, I can do this. I can do 36 pi over 4 pi. That's totally a legitimate algebraic move. If you have 2 roots in a fraction, you can just make them into 1 root. And that's what? Root 9? Root 9, all right, pi's canceled, 36 divided by 4 is 9. So root 9 is really 3. So this and this are going to become a 3. I'll just slap it right there. So what do we get at the end of this? 30. 30. Now, 30 what, though? Volume over time is our answer, is our units. So how do we measure volume? Cubic feet, and then per second. All right. This sphere is growing so that its surface area is increasing at a constant rate of 20 square feet per second at exactly the moment that the radius is 3, right? Because that's when this happens. At exactly the moment the radius is 3, the volume is changing at that instant at 30 cubic feet per second. A little more involved than the last one, would you agree? Okay. Now I want to show you a slightly different approach. Okay, some students like this other approach better. You just have to, you'll tell me, okay? Let's go all the way back to the point where we were trying to find the equation, okay? Remember when we were trying to find the equation? And what we had was, we had 2 equations, right? We had the volume equation and we had the area equation. So we were trying to come up with an equation. We had volume is 4/3 pi r cubed, and we had area was 4 pi r squared, right? And what I did was I solved this one for r and then plugged that back in here and we had an equation, yes? I'm going to show you a slightly different approach. You may or may not like this one more. All right, here we go. Here's what I'm going to do. I'm going to take the derivative of this one with respect to time. I get dv dt equals now 4/3 pi is a constant. And then I take derivative of r cubed, which is 3r squared times dr dt. Now that's the important thing you have to remember, that you're differentiating r with respect to time. So this r cubed derivative is going to be this. Yes? There's a problem already. We don't know anything about dr dt. We know nothing, right? We haven't been given that at all, and it's appeared in our formula. That's not good. But just hang tight. We're going to take this and differentiate it. dA dt is equal to, let's take derivative of this. So 4 pi stays, 2 comes out, and we have r and then what? dr dt again. Okay. Again, we have dr dt twice, and we don't know what it is. Now, what is it we're trying to solve for here in this problem? The dv dt, right? I want this, right? So in order to figure out the rate at which the volume is changing with respect to time, I need to know the radius, and I need to know dr dt. Now, do I know the radius? Yes, we did that already. That was 3. You could calculate that. I don't know dr dt. However, look at this equation. Do I know dA dt?
Yes.
What is it? 20 equals 4 pi times 2 times, so 4 pi times 2 times, now do I know r? Yes. 3 times dr dt, which I don't know, do I? However, if I do this, can't I solve for dr dt? This is 20 equals 8 times 3 is 24. I can't do it today. 24 pi times dr dt. And then you divide both sides by 24 pi. So what is that? It goes in there. I can't do math today, I'm sorry. 5 over 6 pi equals dr dt. Agreed? Do y'all see what I'm doing? I'm solving for dr dt using this equation to take that answer and pop it in right here so I can get this answer. So let me see if that works. Now I'm going to write this equation down, dv dt. I better get 30 as an answer. 4/3 pi times 3. Now, do I know r squared? Yes, that's 3 squared, right? And then dr dt is 5 over 6 pi. 5 over 6 pi. Pi is on the bottom. Okay, this better turn out to be 30. We were going into this formula.
Yeah, it's cubed.
Oh, yeah, you mean those together?
No, just.
No, it's 4 pi r cubed. No, it's 4/3 pi r cubed.
No, but this was the derivative, right? This was the derivative I'm working with, which is why it was squared. Okay, let's see what happens here. These 3's are gone. The pi's are gone. Let's see, this 6, this is a 3, this is a 2. 10. It's 90 over 3. 90 over 3, which is 30. Double check that, right? 9 times 2 times 5 is 10, that's 90. Yeah, it's right, 30. Okay. Any preference there? What do y'all think? Do y'all care?
That one was kind of easier.
This one seemed like we didn't have to, like, seemed, yeah. But you have to understand what you're doing when you're setting this up. You have to realize you're going to use the two equations. One of them is going to have a piece that you don't know anything about, but the other equation is you're going to be able to solve it for that missing piece. So it's like you're almost using an intermediate variable to come back and solve this part right here. All right, well, you know, it is what it is. You can see, I think you can see why calculus students say that this is the hardest section. Let's try something new. Let's get away from the sphere. Let's do a different geometric situation. The plane flying overhead. Okay, so just so you're aware in this example, we are going to assume that the Earth is flat, not round. Yes. Curved, no curvature to the Earth. Flat.
He's a believer.
And
There's people on YouTube for this.
yes, yes. I don't think I've watched a video about flat Earth, but
But they're serious. It's the worst part about it. They have like conventions. They have conventions where they get together and discuss this in like real forums.
yeah, let's not get into it. A plane is flying horizontally at an altitude of 2 miles and a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment the plane is 6 miles from the radar station, how fast is the distance between them changing? All right, so we need to draw a picture first. Let's see if this marker is any good. Well, not bad. Okay, here comes a picture. This will be my plane. Here's the ground first. Here's the ground, and then here's a little radar station right there. If you want, you can show off your artistic abilities. I know. I've been doing this for a long time. Okay, so then your plane It's obviously an F-16. And our plane is flying overhead like this, right? So that plane is moving in that picture. This is my general picture. Then I have the instant in time, which is going to basically be the same picture. If you can't draw a plane as good as I can, don't worry about it, okay? All right. So can anybody help me label any of these pictures or add anything to them that would include some information that I have?
The height of the plane is 2 miles.
The height is 2 miles. Is that going to change in either of these pictures?
No.
No. I'm assuming that
You can put it
the height doesn't change, right? The altitude. So I know the distance from here to here is 2 miles. And I can say the same in this picture, 2 miles. Anything else?
you can do a vector of 600 miles per hour.
Okay, so the 600 miles per hour it's not a length of anything, right? It's just representing how fast the plane is moving. So why don't I do this? Just above the plane, I'm just going to put, 600 miles per hour, with an arrow like that, just to keep us, kind of thinking that this plane is in motion, all right? Anything else?
In your instant, you could plot that it's 6 miles from the radar station.
Okay, good. So in the instant, at the moment the plane is 6 miles from the radar station, how fast is the distance between them changing? I can put 6 somewhere here. Where though?
In the distance from the aircraft to the radar station.
Okay, so you're saying like from here to here
That should be 6
is 6 miles. Do y'all agree with that? Some students will put the 6 down here, but it's not the distance from the plane projected down to the ground out. It's not 6 miles here. It's the actual straight line distance from the radar station to the plane is 6 miles. All right? What else should I put up here? I'm really trying to let you guide me through this now.
Still, maybe just keep the vector of 600.
I want you to think about it. Think about it for a second. I've got to take this one. Hello? Yes. All right. What do you want me to put up here? What have I not put up here?
What you want.
Okay, there we go. What I want,
You want the distance.
and
aircraft's travel.
also
That's given.
what I'm given. Okay, that's what I was looking for.
I'm given the speed and the distance.
I'm given the speed.
The height.
600 miles per hour is the speed, right?
Yes.
So it's a derivative. It's the rate at which something is changing. But what?
Speed over time, something like that.
Yes, it is distance over time, but it's, look, like in the last problems we had, it was like dv dt, right? And the v was the volume of the sphere. Or dA dt, where it was the area of the sphere. 600 is d something dt, right? I'm gonna put it here. It's d something dt is 600 miles per hour. Yeah, but what is this missing piece here? I heard x.
Would you name it velocity or would you name it speed?
DS.
I think it was velocity.
It's well, it is a velocity. D something dt is a velocity, but I don't want to call it dv dt because
DT.
No, it's not speed.
this has to be something changing on my picture that I can see it. And
Well, it's location.
okay, so I've heard x, and that's correct. I can do x, but I'm trying to get everyone to see.
Yeah, I see what you're saying, because it's flying over an X plane, because we're going directly directly overhead, so it isn't.
If I put x here, you need to show me x in the picture. Where is x? What is x?
6 miles north, 2 miles up.
Okay, let me help you with this. Let me help you.
2 miles.
6 miles from here to here, right? That distance is changing in that picture, isn't it? And since it's changing in that picture, I'm going to draw it, and I'm going to call it, let's call it h for like, well, I'll just call it h. It's not x though, right?
No.
X is not changing. That measurement right there is not changing 600 miles per hour. However, can you open that? However, I could add a little more to that picture over there. That would include x. Do y'all see what I could draw? Okay, this is moving, right? 600 miles per hour. So x, maybe you just have to see it for the first time. Now, think about this. If this point is fixed, and this point is the aircraft, do you agree that this point is moving at 600 miles per hour?
Yes.
That x is changing. 600 miles per hour is the rate at which x is changing. Yes? Y'all agree with that?
Yep.
Okay. Now, I do have a little bit of a problem in terms of the sign, plus or minus. Because is x shrinking or growing in this picture? It's shrinking, right?
The question is growing, or from, I guess it could be either or.
Moving towards the radar station, right? Now, I could be on the other side. Okay, so I could have drawn the picture like this, where the plane is on this side and it's already past the radar station, and now x would be growing. Does that make sense?
Yeah.
The good news is this. Either way you do this, you're going to get the same answer, except the sign might be different. Okay, a positive or negative. For the sake of my picture, I'm going to change dx dt to negative 600. And the reason I'm doing negative 600 is because it matches my picture. X is shrinking here in my picture, right? So the rate at which x is growing is negative. One side's coming in. Yes? Sure? Everyone's good with that? Okay. What do I want? I want the rate at which the distance between them, how fast is the distance between them changing? I want dh dt at exactly the moment what? That what's 6 miles?
The aircraft.
That h is 6. That h is 6. Got it? Equation? Okay, so you can use a Pythagorean identity here, right? Isn't this a right triangle? And this side is 2, isn't it?
Yes.
We'll put h on the outside now, okay? You have a right triangle, don't you? With one side being 2. So by the Pythagorean identity, we know x squared plus 2 squared equals h squared. And that is a nice, clean formula, isn't it? See, this is the thing about these problems. Like, you're sitting here, you're reading this, you're trying to draw things, you're trying to, and they're like, whoa, there are right triangles going to work in this. There's the formula. Like, you never know where these formulas are going to like come from. Like, every problem is different. So what if you didn't know the Pythagorean identity? That must have been an easy pre-cal class you were in.
Last semester.
Yeah, okay, so differentiation time. I think we have everything we want here set up. So let's take our derivative here. We're differentiating with respect to time again. What's derivative of x squared with respect to time? 2x dx dt. Plus, well, do I need it? Derivative of 4? 0, right? Okay, equals derivative of h squared. 2h dh dt. There's our equation. I can divide both sides by 2, right, just to clear it out. I don't need it there. So that's the equation I'm going to work with. Let's put some check marks. And I'm going to go with the things that I know. I know dx dt, don't I? So this one I've got. I know at the moment h is going to be 6. I've got that one. dh dt is what I'm looking for. I've got that. The only thing I don't know in the problem is this, x, right? But now we're allowed to fix everything, aren't we? Like everything can be snapshotted now? Where is x in my instant picture? Well, I hadn't drawn it, had I? Wouldn't this be x? Right, so let's take a look at that triangle again. Looks like this. 6, 2, and x. And you can solve that for x, can't you? Okay, let's solve that for x real quick. See, I need x, but I got to go get it. I got to go work for it a little bit. So this tells me x squared plus 4 equals 36. When I square everything out, move the 4 over. X squared is 32, so root 32. All right, take square root on both sides. So I'm there. Questions? Because I'm about to plug everything in. Any questions? Okay, rewriting this, x was root 32. dx dt was negative 600. All right, equals h, which was 6, and then dh dt, which is what I'm trying to solve for. Let's divide both sides by 6. So you should get negative 100 root 32 equals dh dt. Yes? That is the exact answer. Can somebody do that on their calculator real quick and get me a decimal approximation? Negative 555. Negative 565?
Yeah.
Okay. Point something? What? What's our unit of measurement here? H is a distance, so miles, and T is hours. So this is miles per hour equals dH dt. It's shrinking. We're getting negative answer because it's coming towards us. So it's kind of like, you know, this is the thing about speed. You know, if I go and I throw this at somebody, right, I throw this marker at somebody, and I say I threw it at like 15 miles per hour, like that means I'm looking at it as moving away from me as being positive speed. The person that the pin is coming towards is, you know, going to look at it as either positive or negative. So it's relative. It's how you want to orient everything. So think about this. Let's say you had a rope attached to the plane, right? All right? And let's say the rope, you can pull it in as fast as the plane is moving, all right? So if I have this rope, it's attached to the plane. If the plane is actually at the same level as I am, right? If I'm at the same height, 2 miles high, then this rope's going to be coming at me at 600 miles per hour, isn't it? But if I'm below the plane, it's going to be coming at me not as fast. And then as it gets closer, what happens as the plane gets closer? Does the speed of that rope increase or decrease?
Increases.
What do you think?
It's directly.
Like what if the plane is almost overhead? Am I pulling at almost 600 miles per hour on that rope? Is it coming at me? It's decreasing. It's actually getting smaller. And then as it goes overhead, then it starts to speed up again. It starts coming out of my hand fast and burns. You get that rope burn. Now, what I think is really kind of profound and what I'm trying to get you to see is you see this formula right here? Okay, look at that formula right there. This right here, okay? I have x times dx dt equals h dh dt, right? If I take that whole side and divide it by h, I would have dh dt here, right? So just divide both sides by h. This formula tells you how fast that rope is coming out of your hand. dx dt is the speed of the plane, isn't it? That's always negative 600. So watch what happens. If x is 0, right? If x is 0, where's the plane? Right above you. And what is this saying about how fast the rope would be coming out of your hand? It wouldn't be. Just at that instant. I mean, think about that. The plane's coming, right? You're pulling in, the plane's coming, and then right at that instant it's overhead. You're not pulling any rope anymore, right? The h, which was this distance here, that right there, the rate at which it's changing at that instant would be 0. It's not. And then as soon as it passed overhead, it would start coming out of your hand, right? This formula shows that that's happening. If x is 0, the rate of change in h is 0. If x is positive, right, then we're going to have a negative number. If x is negative, meaning x is over there now, plane's over there, now you're going to have a positive speed. So everything is in this formula. It's actually kind of remarkable that it's all here. All right, well, next example. Let's take a poll. And you don't have to answer. This would be a great time to have little clickers. So you don't embarrass yourself. So you're not ashamed, humiliated. So how many of you feel pretty comfortable with what we've done so far? Okay. What's that?
Like including the last problem?
Yes. What's that? Not yet. Yeah, not yet. Okay, how many of you feel like halfway okay with this? Okay, good. So, and how many of you feel like terrified that this is really, really bad? I guess the other end. So I'm only giving you 3 options. Good, kind of good, not really good, but, and then uh-oh. So everyone feels uh-oh about this pretty much? Yeah? Yeah. Okay. Well, that's a natural reaction. So here's the picture of exactly what was happening. So the plane was flying overhead, and the red is measuring the distance between the radar station and the plane. And it's hard to see it from here, but the rate at which this is changing is not the same all the time. But it's the rate at which it's changing is what I'm trying to get you to pay attention to. Let me slow it down just a little bit. Let me see here. Just try counting. 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's hard to tell. It looks like it's counting at a constant rate, like a clock. But it's not. According to the formula, it's not. Because the only way that this would be a constant is if when we solve for dh dt, we got a constant. But we didn't. Like after we took the derivative, if we would have got a constant, then that would be the only way we could tell that that's always the same. All right. Let's try a similar problem. A plane is flying horizontally, altitude of 2 miles, and a speed of 600 miles per hour. Same plane, okay? The plane is headed directly over a ground-based radar station. At the moment the plane is 6 miles from the radar station, hey, same problem. How fast is the angle of the tracking radar changing? So totally different problem. Instead of now me trying to figure out the rate at which the distance between me and the radar station is changing, I need to look at the angle between the angle and how fast the angle is changing. Let's take a look at the picture first. I'm kind of going to give it away when I show you the picture. But I want you to pay attention to the angle and how it grows. Let me slow this down. And let's pause it and let's take it back. Okay, we're going to play this, and I want you to look at this number. Can you all see that enough? 5.7. I want you to notice how fast it changes. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Speeding up, right? Speeding up really fast, and then as it goes past you, right? Look at how the angle changes. Now, can you see why that is happening? If I'm looking at this thing down there, right? It's real far away, but as it gets closer, right? I have to. Here we go. Now you can see my head moving, right? Right? You could also think of like a car going by. You know, you see it way down the road. You know, and you're like, and then, you know, and then you're not having to turn as fast to keep up with it anymore, right? That's the idea here. So now, this is actually, you can imagine that this would be important if you're trying to shoot this plane down, right? Like, right? I mean, if you were trying to shoot this plane down and you had some computer trying to calculate how to lead into this, right? If you're doing like anti-aircraft, not missiles, but like just artillery, not artillery. They call it artillery, but whatever.
The failing system, like the thing they have on the boat.
Yes, the failing. That's just a bunch. They're just throwing out a bunch of lead.
Yeah, it actually
Okay.
tracks ahead of it.
That's right. So, but it has to know how far away it is, its speed, and then that way it can calculate how fast it needs to be turning in order to keep up with it. Look, we can laugh about it, but we all know that our need to kill each other has motivated technology beyond anything else, right? I mean, it is, yeah, so, but we're going to look at a little more, you know, a little less military perspective here. We're just going to watch this plane go over and see how fast our head is rotating, all right? Do you understand the difference in this picture, in this problem compared to the previous one? Okay. All right, so let's get our pictures going here. It's the same picture, but not the same picture. I mean, you still have the ground-based radar station, you still have the plane, right? You still have in the second picture the 6 miles, right? That you still have. So our general. This is our instant. This is what we are given. This is what we want. And this is our equation. This format that I've been giving you will work 90% of the time. All right? There are some problems that this won't work with, but has anyone started watching the homework solution videos for this yet? Okay. Yeah, 48 hours. I mean, all right, so if I label this 6 here, I'm going to label this over here H. Do I still have 2 miles? I still have that. So I'm going to do this. Drop this down. I'm drawing my triangle this way this time. This is 2. And I'm doing that because I hope you can see that there's my angle. I'm going to call it theta. That's my angle, right? It's formed from this triangle. Agreed? And then this over here, I'm going to drop this one down. I'm going to call this 2. Now, if I took a snapshot picture, and this is 2 and this is 6, is that angle fixed? Yeah. Yes, it is. I can figure out what that angle is. I'm going to have to go back to pre-cal to do that, but I can figure out what this angle is. We will have to do this, all right? We might get around it. Let's see. Okay, let's proceed. What are we given?
Everything that's given.
What are we given?
We're given the distance from the radar tower, which is the hypotenuse, and the height, which is going to be
DXDT.
We still have dx dt. we still have dx dt is negative 600, don't we? But there's a problem because x isn't on my picture yet. So where is x on my picture? It's the ground. Watch. This right here can still be x, right? Because if this plane moves, the base of this triangle is changing, isn't it? It's keeping up with the plane. So putting x down here is perfectly fine to have it down here. The reason I have it down here instead of up here like last problem is because I needed this angle, right? So my triangle is going to look like this instead of like that. That make sense? Okay. And I even know right here that if I had to, that's root 32, but I only know that from the previous problem, right? What do I want? How fast is the angle changing, which is d theta dt? When I was in graduate school, one of the things that I was tasked in doing was doing the recitations for calculus classes at the university. So I got paid, but it was what I would have to do is what they have in the university. Usually, you go to calculus lecture, and then one day a week, like on a Friday or something, you go into like an hour and a half Q&A session where you just go and sit down. If you have a question, there's someone that goes up there and answers your questions. Like we'll work out problems. And I can remember that when I first started doing that, those sessions, that was like the most nervous I ever was. Because, I mean, imagine walking into a class, there's like 80 students in there, and they can basically ask you any question from the book and ask you to work it, you know? This stuff, like, it takes a long time to get really good at this stuff to where you're comfortable with it. So I understand if you feel uneasy, that's normal. You want to work to a point where you feel pretty confident about things, but it would take a lot longer than one semester to become an expert in this, if that makes sense. All right? So, all right, d theta dt is what we want. At when? At what moment? What's 6 miles? H is 6. So notice every time I've done this, I've said at and I've specified the variable and what its value is, right? I never just say like at 6 because you need to know what this is going to be replacing later, right? All right, your turn to come up with an equation. Anything that relates x and theta together off of your general picture. You can do, well, sine will be, if you do sine of theta, it's going to be opposite over hypotenuse, and that doesn't have x in it.
Oh, we have to have it.
You have to have x in it, right? You need to have x and theta connected. Tangent. Tangent theta will work, won't it? So I have an equation that says tangent of theta is what? 2 over x. That's an equation, right? That's the equation off of this triangle. Tangent theta is 2 over x. So if I can differentiate that, I should get a d theta dt to pop out. I should get a dx dt to pop out somehow. Questions? Okay, this is the calculus part. I need to differentiate that, right? Now, I think before I differentiate that, you don't have to do this, but I'm going to see if you like this or not. I'm actually going to clear out the x from both sides, or from the right side, by just multiplying both sides by x. Is that okay with you? Just so I don't have to work with, this is really like x to the negative 1 power, which I could differentiate, right? But if I just multiply both sides by x, it's this. And now let's differentiate that. And I'll do it. We already have all this information. Okay, if I differentiate that, how do I have to do it? Product rule. Product rule. This is a product, right? So you do derivative of the first one times the second one plus derivative of the